Assalamu alaikum wa rahmatullahi wa barakatuh. Inshallah, today I'm going to talk about Schwarz lemma for the holomorphic function, and then we will see some consequences of this lemma, and after that we will solve some simple examples. Let's start. The first result for our video is we have the function f. This function is an analytic function with a condition f0 is equal to 0. So we have a condition here, f0 is equal to 0, and the modulus of f is less than 1, and this condition is it's included in this function. If we say that f from d to d, so we have the modulus of f is less than 1. So if we have the function as analytic and f0 is equal to 0, it's very important condition here. So we have three conclusions here. Be careful from these conclusions because we want to see what about this conclusion. The first one, f of z, the modulus of f of z is less than or equal to the modulus of z. The second conclusion here, the modulus of f prime 0 is less than or equal to 1. And we can say that this is the Schwarz lemma, I and double I. And we can say that these inequality are sharp. What is the meaning of sharp inequality? The meaning that there is some function f of z that make these two inequality to be equality. So we have f of z less than or equal to z. There is another function, there is some functions f of z such that make this function, this inequality will be equal. And make this inequality will be equal one. So we have the function f of z. This is lambda z. For the f of z is lambda z, we have the equality of these inequalities. We call it extremal function. So the third part, f. These two inequality will be equality. F prime of 0 is equal to 1. If z naught is equal z naught for some z naught in d and z naught not equal to 0, then the function is equal lambda z, and the modulus of lambda is equal to 1. It means that we can say that lambda is equal ei theta. This is a rotation. So what's the idea? The idea here to construct a function. So the idea of all of these type or consequence of Schwarz lemma. So define a function, define g of z. This function, construct f of z over z and f prime 0. Construct these two parts and apply the maximum principal theorem. Maximum principal theorem. This is the idea of the proof of this lemma. So let's see, how can we construct the function g of z to find f of z over z and f prime 0, because we want to prove these two inequalities. So let's start from the Taylor expansion. Why? Because we have the function is an analytic function. So we can say that let f of z, we can define it f0 plus f prime 0 over 1 factorial z plus f double prime 0 over 2 factorial z square plus f triple of 0 3 factorial z cube, and so on. Why we can write this one? Because the function is analytic. And we have an assumption here, f0 is equal to 0. So we can divide f of z over z. So we can divide f of z over z. Why I divide this one? Because I want to conclude f of z over z is less than or equal to 1. This is equal 1 f prime of 0 plus f double prime of 0 over 2 factorial z plus so on. So now the idea, how can we construct the function g? So we can say that let's define g of z. What's g of z? We can divide it from this part. We can write it f of z over z. Why I choose this function? Because I want to prove f of z less than or equal to z. It means that f of z over z less than or equal to 1. So I want to construct the function g. And here z not equal to 0 because we divide by z. And also if we take the limit here, when z goes to 0, we can say that all of these terms is equal to 0 except the first one, f prime of 0, when z is equal to 0. Be careful. This function g of z is continuous function on the unit disk and also analytic function on the unit disk. Why? Because we want to apply the maximum principal theorem. And to apply a maximum principal theorem, we apply it for analytic functions and continuous function on the domain. So here we can say that this is continuous on D and analytic on D. Means that we can delete continuous because if it's analytic, so it's continuous on the region. So this is the function g of z. Now we want to prove or we want to apply the maximum principal theorem for this function. I want to ask a question here. Is the function g of z is a constant function? No. So the suprema or the maximum value of the function g lie on the boundary. Because what's the function or the maximum principal theorem here? We can say that if the function g not constant function, it's not a constant function, so the maximum value of the function g lie on the boundary. This is the first one. But if the maximum value of g lie inside the region, so we can say that g is equal to constant function. But here it's not a constant. So if we want to applying the Schwarz maximum principal theorem, so we can say that applying maximum principal theorem, this is maximum principal theorem, we can say that the suprema of over z is in D closure. What's the D closure? This is a D closure. This is a unit disk with the center 0 and radius 1. This is D, and the closure we take the boundary here. But if we write it, this is another disk with the radius r, so we can say that the modulus of g is equal to the suprema when the modulus of z is equal to r, the same g of z. Why? Because we're applying the maximum principal theorem. The maximum or the maximum value of the function g lie on the boundary. So let's go back for the function g. What's the function g here? The function g is f of z over z. So let's see. This is equal the suprema when the modulus of z is equal to r, the modulus f of z over z. Can cancel this one. So here, the modulus f of z over z, and this is less than or equal. We have f of z is less than 1, and we have the modulus of z is equal to r. And by maximum principal theorem, this one goes to the boundary. So it means that when r goes to 1. So when r goes to 1, this goes to 1. So the supremum of g of z is less than or equal to 1. But we have the function g itself is less than or equal its supremum. Its supremum, g of z. And the supremum of z of z is less than or equal to 1. So g itself is less than or equal to 1. So we can say that g of z, the modulus, is less than or equal to 1. This is our result. Go back to the definition of the function g. We have two branches here. The first branch we can prove I, the second branch we can prove double I. So from we can write it 1. So we can say that from 1, if we substitute by the function g is equal the function f of z over the modulus of z is less than or equal to 1, it means that the function f of z is less than or equal the modulus of z. This is the first one. After that also, this is when z not equal to 0. And when z is equal to 0, we have the modulus of f prime of 0. This is g of z is less than or equal to 1. This is when z is equal to 0. So this is I and double I. This is the main idea. So the main idea here, to define the function g from the Taylor expansion and look at what you want to prove. Here I want to prove f of z over z. So we have f0 is equal to 0. This is the first term that I have. So it's easy to prove this one. Now, we want to prove that there is an extremal function. Extremal function, it means that this is a function that make these inequalities equalities. So instead of fz is less than or equal to z, so we want to fz is equal z. So let's see. This is the second part. So to prove the triple I, here we can say that prove this inequality is sharp. What's the meaning of sharp? Sharp, it means that what's the function f that make this less than or equal, that make it equal. So we call it sharp inequality. So let's see. Here also it's the same. It's the same. The suprema. So you have there is exist z naught in D and z naught equal to 0. So we can say that if the modulus of f of z naught is equal the modulus of z naught, means that the modulus of g z naught is equal to 1. Or f prime of 0 is less than or equal to 1. It means that the modulus of g is less than 1. So let's see. We have the suprema z in D closure, the function g of z. It's the same. But this suprema, it's the same, the value. I have the value here. I have the value. So it means that it's equal the modulus of g of z naught. Or it's equal the modulus of g0 when z is equal to 0. But both of them is equal to 1. What's it mean? It means that by using the maximum principal theorem, g is a constant. Because g here, the modulus of g is equal to 1. So it means that g of z is equal to, we can say that the modulus of g of z is equal to the modulus of lambda is equal to 1. And we can write g itself, g is constant here. Because we have the supremum is equal to 1. Equal to 1. So by using the maximum principal theorem, g is constant. But if g is constant, so we have f over z is equal to lambda. What's the lambda? This lambda because the modulus of this one is equal to the modulus of g. So f is equal lambda z, where the modulus of lambda is equal to 1. Why? Because we can write it, take the modulus here, we can find the modulus of g is equal to the modulus of lambda is equal to 1. And this is for all z in D. Why? Because we take z naught as an arbitrary point. So this is the first result for us. So the first result is we have the function. This function is analytic function. And we have an assumption f0 is equal to 0. It's a very important assumption. So we have three conclusions. But now there are a consequence of this assumption. If we add another assumption, f prime 0 is equal to 0, how can we define the Schwarz lemma for this case? If we add another assumption, f of 0 is equal to 0, f prime is equal to 0, f double prime is equal to 0, how can we define the Schwarz lemma for this problem, and so on? So this is the main idea. This is the main idea. What about if we take the f is analytic function, and we have f0 is equal to 0 and f prime is 0 is equal to 0. The same idea and the same things. I'll take it copy. This proof, I'll take it copy and put it here. The same one. But here, instead of divide by z, go back for the Taylor expansion, instead of divide by z here, this term also will equal to 0. So the first term with us is the third term. So here we divide by z squared. So here f of z over z squared. And here f double prime over 2 factorial. And so on. And repeat the same proof. Let's see, I will copy it and we'll go back. So I'll copy it. Here, this is the first one. Define the Taylor expansion. Define g of z. And after that, using the maximum principal theorem to conclude what's the Schwarz lemma for this case. Let's see. So let's see. Here, what about if we have an analytic function, f from d to d, and f0 is equal to 0, f prime is equal to 0. So we have this one and this one, both of them is equal to 0. So the first term here, we have this term. So our function, we divide by z squared. So f of z over z squared, this is our g. So define g and use the maximum principal theorem and done. So here, f of z over z squared. So here we use f of z over z squared when z not equal to 0. But when z is equal to 0, take the limit. This limit, both of them, all of these terms is equal to 0 except this one. Here, after we divide by z squared, we have f double prime over 2. This is 1. So applying the maximum principal theorem and done. All of these steps, we did it before. So we have the supremum g of z is equal to the supremum z is equal to r. What's g of z? F of z over z squared. Here z squared, the previous result over z. Here 1 over r squared. The previous one 1 over r. The same thing. But here g of z is less than or equal to the supremum of it. So the modulus of g is less than 1. Go back for the definition of the function g. We have g is f of z over z squared. So f of z over z squared less than 1. And f double prime 0 over 2 factorial is less than 1. Be careful. Here it's not over 1. Here f double prime less than 2, not 1. So we have f of z less than or equal z squared. This is Schwarz lemma for this case. So in some of comprehensive exams, there is a lot of question about this consequence of Schwarz lemma. It is that we have the function is analytic function, and we have f of 0 is equal to 0, f prime is equal to 0. Prove f of z is less than z squared, or f double prime is less than or equal to 2. Both of them. Or he asked about what's the function? What's the function when these two inequalities are equal? So let's talk about the third conclusion. Let's see. Here, the third conclusion is the same. To prove that this inequality is sharp, we have z not is not equal to 0. F of z equals z squared. This is the only things that we change. So we have g of z naught is equal to 1, and f double prime is less than or equal to 2. Here equal to. Here this is equal. So we have the supremum of g is equal to 1. So g of z is equal to 1, the modulus of a lambda. So we have f is lambda z square, and the modulus of lambda is equal to 1. Done. The same previous one. So we can add another assumption for that. We can say that f0 is equal to 0, f prime 0 is equal to 0, f double prime is equal to 0. The same thing. The same thing. Here f0 is equal to 0, f prime is equal to 0, f double prime is equal to 0. So the first term here with us is f triple prime, z cube. So we have to divide by z cube. So g of z is f of z over z cube. F triple 0 is over 3 factorial here, or here 3 factorial. And applies the maximum principal theorem, and done. The same thing. All of these consequence, we will see it in the comprehensive exams. We will see all of these questions. So let's see, applying the maximum principal theorem, the same things. Here, instead of f of z over z, we divide by z cube. Instead of 1 over r, we have 1 over r cube. All of this goes to 1. So substitute by g of z with f of z over z cube. So f of z is less than or equal to z cube. This is the first conclusion. So the second conclusion, we have f triple prime over 3 factorial less than 1. So multiply by 3 factorial, we have f triple prime 0 is less than or equal to 6. It's very easy to get it. So we ask about the equality. So to prove the inequality is sharp, it's the same. This is equal, as we said before. This is equal. So we have f of z naught is equal z naught cube, and f triple prime is equal to 6 or 3 factorial. So we can prove that f is lambda z cube. It's the same. F is equal ei theta z cube. It's the same thing. So let's see more general. This is that we can take it in our final exam. If we have the function f is analytic function, and we have f0 is equal to 0, f prime is equal to 0, f double prime is equal to 0, till fn minus 1, 0 is equal to 0. So all of these terms, we cancelled all of these terms. All of these terms will equal to 0. And the first term that we have, this term. So what's our function g? Our function g, f of z over z of a power n. So f of z over z of a power n is equal, if we take the limit, if we equal fn, the derivative of n at 0 over n factorial. This is our z when z is equal to 0. And apply the maximum principal theorem and done. So our function here, our conclusion here, f of z is less than or equal z of power n. And fn, the derivative of n at 0, is less than or equal n factorial. And done. Let's see. So here, the supremum, here f of z over z of power n, less than 1 over rn, take r1 is equal to 0. So we can prove this one and this one. The same that we take it before, the same one. By the way, I take it copy from the previous slides. It's the same one, the theme. But we can see all of these consequences in the comprehensive exam or the exams of the previous terms. So to prove the sharp, this is equal. To prove the sharp, we can prove that f of z is lambda zn. The same thing. So this is the first part. This is the first part of our video. Let's see if something will be different here. If we have the function is analytic, and we have f0 is equal to 0, and fa is equal to 0. So here, I want a map. This map takes a to 0. I want to take a to 0. Here, what's the function f? G, to apply the maximum principal theorem. So before we start from this problem, we can define the map phi. It's very important, this map. This phi will take a, d to d. So I want to map the unit disk to the unit disk, but also I want to take A to 0. It's very, very important. Let's see. And after that, we'll go back for this problem. Let's see. So we can write very important. And by the way, after that we'll see a lot of maps for these examples or problems for Schwarz lemma. If we have another map different from this map, choose another name. Here for this map, we define it by phi. If we work on Schwarz lemma, when you see phi, look at this map. But if we want to use another map, as like the homework, so we'll choose another map to map the upper half plane to the unit disk, the lower half plane to the unit disk, the right half plane to the unit disk. If we use any map, call it another name, call it epsilon, instead of this notation. So we notation with this one, phi. So here we define this map, it's very important, phi A of Z. We define this map. This is equal Z minus A over 1 minus A conjugate Z. Here, this map, what's the properties of this map? Here, this map, we can say that this is an automorphism from D to D. Automorphism means that there is a bijection from the unit disk to the unit disk. So we have an automorphism, phi, on delta. You can say that this one. You can say that phi is automorphism on delta or on D. Means that phi, it is a bijection from D to D. We define it in this way. What's the properties of this one? The properties of this one, are the follows. The first one, we have phi A of A is equal to, if we substitute with Z is equal to A here, we can say that is equal to 0. So it's very important that phi take A to 0. Very important. The second one, we have the modulus of phi A of Z. The modulus of phi A of Z. What's the modulus of it? The modulus of phi is equal the modulus of Z minus A over the modulus of 1 minus A bar Z. So let's see. Of course, we will see the modulus of phi on the boundary. On the boundary, the modulus of Z is equal to 1. On the boundary, mean that if we take it, you will see the following. Take Z outside, so we can take Z outside here. If we take Z outside, mean that 1 minus A Z conjugate over 1 minus A conjugate Z. The modulus of Z is equal to 1. Because we'll talk about the boundary. Here, this property is the second one. We talk about the modulus on the boundary because it's very important. We'll use it. Here, the numerator and denominator, this is the conjugate of the denominator. If we take the modulus, it means that this is if we take the modulus of Z, it means that the modulus of Z bar. It's the same. So here, this is a conjugate of this one, so it's equal to 1. So it's very important. The third one, this is the important one. If we call it phi A of Z minus 1. Minus 1. It's the same phi minus a of z. It's equal z plus a over 1 plus a bar z. Okay? And this phi minus 1, where? Phi minus 1, take a of 0 is equal to a. Because phi take a to 0, and phi minus 1 take 0 to a. It's very important. We'll use it after that. So this is some properties of the map or the automorphism map phi. Now, what's the question? The question is that I want the Schwarz lemma. I want what's the shape of the Schwarz lemma if we have the function f from d to d, and if 0 is equal to 0, and if a is equal to 0. How can we define it? Here we define from if a is 0 is equal to 0, we can define f of z over z. But again, we want another part. We want to take a to 0. So here we have to divide by phi a of z. This is our idea. So here, our function d, so define g of z as f of z over z phi a of z. Be careful from this question because it's we find it a lot in the comprehensive exam or in the exam itself, in the final exams. So we have g of z is f of z over z phi a of z. This is, be careful, this when z not equal to 0 and z not equal to a. Why? Because for a, the denominator is equal to 0 here. So this is g of z. Now, if I ask you, this is to conclude the first part, to conclude this part. F of z is something. But what about the second one? The second one here, I have 3 conclusions, not 2. For the first part, we have 3 conclusions, not 2. The first one, what's the modulus of f of z? What's the modulus of f prime 0? What's the modulus of f prime a? It's very important. So here it's very important to take the limit. So this is the first one. The second one, take the limit when z goes to 0 for the function g, and take the limit when z goes to 8 of the function g. Why? Because I want to define g of z as, this is the function, when z not equal to 0, when z not equal to a, the function when z is equal to 0, the function when z is not equal to a. So this is our g. And after that, use the maximum principal theorem to conclude these 3 parts. So let's see. This is equal limit when z goes to 0, f of z over z, and divide by phi of a. This means that we can write the numerator and denominator here. It's 1 minus a bar z. Here z minus a. This is our function. Take the limit. This limit is equal f prime 0. And this limit is equal, if we substitute with 0 here, we can find it minus 1 over a. So is equal minus f prime of 0 over a. This is the first one. The second one, when z goes to a, g of z is equal to the limit when z goes to a. Here, if we divide it, this one, I'll take z minus a instead of z. We can write it f of z minus f of a. F of a is equal to 0. From here, f of a is equal to 0 over z minus a times 1 minus a bar z over z. Here, what's the value of this one? The limit of this one? It's equal f prime of a times, here if we substitute with a, is equal 1 over This is 1 over A. Mean that 1 minus the modulus of A square over A f prime of A. This is our function. So here we can define the function g in 3 parts. Let's see. Oh, this is a general one. If we have if A is equal to 0, if A2 is equal to 0, and so on, we can say the same one, the same thing. But let's see. Let's complete this one. So we can define g of z. It's equal 3 parts. The first part, f of z over z times phi a of z. This is our function, with z not equal to 0 and z not equal to a. Second one, when z is equal to 0. The third one, when z is equal to a. This is the limits. This is the limits. So here is equal minus f prime of 0 over a. And here we can write it 1 minus the modulus of a square over a f prime of a. And use the maximum principal theorem. Here we can use the maximum principal theorem and do the same things. So here, using the maximum principal theorem, that we have the supremum of the function g of z. The same thing, z is in deep closure, is equal to the supremum when z is equal to r, g of z. And we have g of z is equal both of these things. So we have the supremum when the modulus of z is equal to r, and r goes to 1. Here we have the modulus of f of z, the modulus of z, the modulus of phi a of z. Here is equal to less than or equal to 1 over r, the modulus phi a of z. When r goes to 1, it means that I have phi goes to 1. When r goes to 1. Why? Because I took the properties of phi is equal to 1 on the boundary. So this is when r goes to 1, this is goes to 1. Both of them goes to 1. So we have 3 conclusions from these 3 parts. The first part is f of z is less than or equal this one, the modulus of z, the modulus of phi a of z. Be careful, this is not equal to 1. This is equal to 1 on the boundary. But here I conclude for all z on the unit disk, for all z and d. Another thing, we have the f prime of 0, if we take the modulus here, is less than or equal to a. And f prime of a, take these 2 things in the other sides, we can get it less than or equal to a over 1 minus a square. So we can talk all of these things. Again, if we write it in this way, what's the function f from d to d? Analytic function. If a1 is equal to 0, a2 is equal to 0, a3 is equal to 0. So here we can define, here I want to write only the function. Here we can find g of z is equal f of z over phi a1 of z, phi a2 of z, and so on, phi an of z. I'll put it here to look at it, but it's the same. It's the same that we take it before. So this is the first part of the Schwarz lemma. The first and the most important part for the Schwarz lemma. Because if you understand this part, it's easy to conclude. After that, we just conclude. So let's see. This is the main result. The second part of the Schwarz lemma here, what about if I want to ignore this assumption, if 0 is equal to 0? if I want to ignore if 0 is equal to 0. So I have only I have f is analytic function from d to d. And I'll ask you, how can I estimate the function? How can I estimate the derivative at 0 or the derivative at any point? It's very important. For this part, we will call it Schwarz lemma. Schwarz lemma, I have the function, analytic function, from d to d, and I don't have the assumption if 0 is equal to 0. This is our case. So we call it from d to d. Idea is very easy. The idea is very easy. I have from d to d. So apply this lemma. I'll go back for this lemma. To go to, this is f. To go back for this lemma, I have a to f of a. So compose it with d, compose it with another d. Here, if I want to go from fa to 0, I'll compose it with phi f of a. We took what's phi? And here phi minus 1. So we can go from 0 to 0. Phi minus 1 f phi, and define the function g to go to the function, or to go to the first result for the Schwarz lemma. Let's see. I have to end this this video and start another one. So in the next video we'll talk about the second idea, for if we ignore this assumption and define the Schwarz lemma, how can I prove it? Let's see in the next video, inshallah. Assalamu alaikum.